So today in class we learned about problems where we need to count the number of different ways of arranging a group of objects. So some problems where the group of objects was supposed to be arranged in a line or a row, and then some problems where the group of objects were supposed to be arranged in some kind of a circular arrangement. What we're going to do in this video is learn how to count the number of ways that objects can be arranged in a row or line when some of the objects are repeated, so when they aren't a bunch of different objects. So what I'd like for us to do is sort of go through basically the normal structure of class. So I'd like you to start with doing a couple do now problems, then we'll do some notes, and then I'll have some practice problems for you to try on your own. So to get started, what I'd like you to do is pause the video and try out these couple of do now problems on your own, and then unpause and I'll explain the problems and you can check your answers. So in the first problem it says Mrs. Runge is arranging her textbooks on her bookshelf. She uses 4 different textbooks for her classes this year. How many different ways are there of arranging the textbooks on the shelf? So you can sort of imagine there's a bookshelf and then there's 1, 2, 3, 4 textbooks and they're lined up in a row. And the question is, if there are 4 different textbooks, how many different ways can you organize those textbooks in a row on the shelf? So some of you might remember the formula from class that if you want to organize n objects in a row or a line or a list, the number of different arrangements is n factorial. So you could just remember that we're supposed to get n factorial, or in this case, actually, we're talking about n is 4. We're talking about 4 different textbooks, so you might have just remembered that the correct number of arrangements is 4 factorial, which, if you plugged into your calculator, would give you 24. But let's just sort of talk through how to reason through it in case you had forgotten that that was a general formula we discussed. So let's think about filling in these 4 slots on the bookshelf one at a time. So let's first think about filling in this slot on the bookshelf. If we haven't put any books on the shelf yet, there are going to be 4 different ways of picking a book to put in this first slot. Now, for each of those possibilities, once you fill in that first slot, there's only 3 books left to fill in the second slot. So there are 4 different ways that you can fill in the first one, and then for each of those, there's 3 other ways of filling in the second one. So we're up to 12 possibilities of how to fill in the first and the second one, because we have 4 times 3. And then, once we've already put 2 books on the shelf, we need to fill in the third slot, and there are only 2 books left to fill it in. So we're going to multiply by 2. And then once we fill in that slot, there's only 1 way to fill in the last slot with a book. So we get 4 times 3 times 2 times 1, which gives you 24. So whether you sort of reason through the problem like this, or whether you remembered the general formula we discussed in class the other day, either way you should get 24. So let's try out the next problem now. So in problem 2 it says, suppose you're setting the table for dinner, you need to set 5 places for your family, and you have 5 different colored plates. How many different ways are there of arranging the plates around your circular dining table? So again, you might remember from yesterday that we had a formula for the number of different ways you can organize n different objects in a circle, and that was n factorial over n, so in this case 5 factorial over 5. However, suppose that you didn't remember that. Let's just sort of try to reason through it a little bit together. So let's draw our circular dining table. And we know that we have 5 place settings. And we know that we're talking about 5 different colors. So let's say that we have red, orange, yellow, green, and blue. So let's first think about the 5 factorial thing. So the 5 factorial thing sort of comes from a similar reasoning from the bookshelf. So let's first think about how many ways we can fill in this first placemat. Well, there are 5 color choices to put at the first placemat when you get started. So that gives you your 5. But then for each of those possibilities, there are going to be 4 ways you can fill in the second placemat. So in total at this point we have 5 for the first placemat, and then for each of those there are 4, so we're up to 5 times 4. Then for each of those that we've gotten so far, there are 3 different ways to fill in the third placemat, 2 ways of filling in the second to last placemat, and 1 way of filling in the last placemat. However, when we're talking about a circular arrangement, one thing that we have to be careful about is rotations of basically the same arrangement being counted as different arrangements. So let me just sort of fill in the picture a little bit so I can give you an example of what I mean. Suppose that this place setting was red, this was orange, this was yellow, this was green, and this was blue. Now consider this arrangement instead. Suppose this one's red, this is orange, this is yellow, this is green, and this one's blue. Notice how those are really the exact same arrangement. It's just that to go from the pink arrangement that I drew to the blue arrangement that I drew, we just rotated everything exactly one place. So that's 2 different arrangements. That's 2 arrangements that count as being different when we do this calculation, but we're really going to consider them the same because like each color would be next to the same color on its left and right. So then we could rotate it again, and we would get a third rotation that we're going to consider to be equivalent, where instead of the red being here or here, the red will be here, and then we'll go orange, yellow, green, blue. We can get a 4th rotation by starting here with the red and going orange, yellow, green, blue. We can get a 5th possible rotation by having red start here and going orange, yellow, green, blue. And if it's the exact same arrangement, it's just like rotated around the table, we're going to treat those as if they're equivalent to each other. So the problem with this calculation is that I just gave you an example of 5 arrangements that are counted as different arrangements in this, but we're actually really going to treat as being equivalent. So this calculation actually gives us 5 times as many arrangements as we're supposed to get. And so what we want to do at the end is divide by 5. And so that's where this 5 factorial over 5 thing came from that I mentioned that you might have known earlier. Now, either way that you plug it into your calculator, you should get the same thing. You should get 24. Oops. Now, remember, if you have your graphing calculator, you need your graphing calculator every single day, the same way that you've needed your graphing calculator every single day all year. If you make a decision not to bring a graphing calculator on any given day in class, you are going to be stuck, instead of calculating something pretty quickly using your graphing calculator that looks like this, you're going to have to, every single time you have a factorial, write out this entire product of numbers, type that entire product into your phone, and divide. And the more complicated the problems get, the more obnoxious it's going to be. So bring your calculator every day. So all this information that was sort of reviewed over the past few minutes is all summarized down here at the bottom. If you have n objects that need to be arranged in a row or line or list, there are n factorial different arrangements. If you have n objects that need to be arranged in a circular or round arrangement, there are n factorial over n different arrangements. And then if you forget what a factorial is, it's basically you take the number and then you multiply by the number before that, number before that, number before that, number before that, until you get down to 1, and you multiply by all those numbers together, and that's whatever the factorial is. So the new thing that we're going to do today is, what if you aren't arranging objects that are different from each other? What if, for example, I had 2 copies of the same textbook instead of all different ones? How would that impact the number of different arrangements that you have in this arranging the textbooks on a bookshelf question? So that's what we're going to be exploring today. So let's get into some examples together. So number 3 says, Mrs. Runge is making a bunch of posters to put up in front of the classroom. 3 of them say, less chatting, more mathing. 1 says, yay math, and 1 just has a smiley face on it. How many different ways are there of lining up the posters above the board? Now, If all these posters were different, we could use the exact same reasoning that we used yesterday to say, well, there are 5 posters, organizing them in a row, and so the number of different arrangements better be 5 factorial. And that's sort of the first step, but it's actually a little bit more complicated than that when you have a few things being repeated. So notice that there are 3 posters that say less chatting, more mathing. So one of these things is being repeated, and it turns out that that makes things a little bit more complicated. So let's draw ourselves a little picture to help us understand what is going on here. Okay. So suppose that the 5 posters are going to go in a row like this. Now let's just take a look quickly at one specific possible arrangement. There are lots and lots of different arrangements, but let's look at one in particular. So suppose we take all of the less chatting, more mathing posters, and they go first. And then suppose we do the yay math poster, and then we do the smiley face at the end. So this is one single arrangement. Here's the problem. Imagine you could take the 3 less chatting, more mathing posters, and suppose you could put a little number 1 on the back of one of them, number 2 on the back of another one, and number 3 on the back of the third. This calculation treats as different arrangements. Suppose you took the less chatting, more mathing poster 1 and you flip-flopped it with less chatting, more mathing 2. This counts that as 2 different arrangements, but if you're just looking at the posters, they're going to look exactly the same. Similarly, imagine you took this poster and flip-flopped them. Again, this calculation treats that as 2 different arrangements, but if you look at it, it's going to look exactly the same to you. So we don't want to treat those as 2 different arrangements. So let's figure out, for a given setup, a given arrangement, how many times does this calculation actually count it? So let's think about that. Basically, it comes down to how many different ways can you take these 3 posters and put them in these 3 slots. So that's basically just a question like yesterday. We're going to sort of completely ignore these guys for just a second, focus on these 3 posters and think about how many different ways can you put these 3 posters in these 3 slots. Well, that's a question from yesterday. How many ways can you line up 3 things in a row? Well, 3 factorial. So for this single arrangement, this calculation counts it 3 factorial times, which is 6. So this calculation counts this arrangement 6 times. We don't want to count it 6 times. We want to count it once. Now that's true for every single arrangement I could come up with. It was arbitrary that I decided that we would look at this arrangement. I could have flip-flopped the yay math and this less chatting, more mathing, and the problem is still the same. And so for every single arrangement that you have, this calculation counts it 6 times. We only want to count it once. And so what we're going to do is we're going to divide by that 3 factorial. And that's going to take each group of 3 factorial arrangements that it thinks are different. It's going to divide it by that number, and so we're only going to count one of them. So if you put this into your calculator, you would end up getting 20. So there are 20 different arrangements of these posters. So let's try another example and think through that one as well. So suppose Mrs. Runge and Miss Tracy share a shelf on a bookshelf in the math office. Together they have 3 Math 3 books, 2 Math 2 books, and 2 pre-calculus books. How many different ways are there of lining up all their textbooks on the shelf? So let's see. So we have 3 Math 3s, 2 Math 2s, and 2 pre-calculuses. So there's a total of how many books? 7. So thinking about what we did yesterday, you might think that we should start with 7 factorial since we're arranging these books in a row, and that would be a great idea to start out with 7 factorial. But then we have to deal with the fact that there are repeats. So there's 3 Math 3s that are all going to look perfectly identical when we're looking at them. There are 2 Math 2s that are going to look perfectly identical when we're looking at them, and 2 pre-calculuses. So let's think about how many different ways there are to arrange those on a shelf. So let's draw a little picture. So I'm just going to draw 7 books on the shelf. 2, 3, 4, 5, 6, 7. Okay, so here's 7 books on the shelf. 3 of them are Math 3 books. I'm going to label them M3. 2 of them are Math 2 books. I'll label them M2. And 2 of them are pre-calc books. I'm going to label them P. So if we look at one specific arrangement, one possible arrangement would be put all the Math 3s at the beginning, then the Math 2s, then the pre-calcs. So that's one specific arrangement. And we look at that and we're like, yeah, that's one possible ordering. The problem is that, again, this calculation counts it more than once. So let's think about how many times this calculation actually counts this as. Well, again, let's imagine that we could open up these textbooks, and out of the 3 Math 3 books, let's imagine we could open them up and label them in a way that would help us to distinguish between the 3 books. So let's call this first book Math 3 1, Math 3 2, Math 3 3. This is Math 2 1, this is Math 2 2, this is Pre-Calc 1, Pre-Calc 2. And let's think about how this calculation sort of distorts how many different arrangements that there are. So let's first think about if we want the 3 Math 3 books to be in these 3 slots, how many different ways can you put those 3 books within these 3 slots? Well, there's 3 factorial ways of doing that. So there are 3 factorial different arrangements that have these books where they are and have these Math 3 books where they are, but this calculation treats them as different because these book 1, book 2, and book 3 are in a different order. Could go 1, 2, 3, 3, 2, 1, 1, 3, 2. So there's a bunch of different orders that you could put these 3 Math 3 books on the shelf in these 3 spots, and yet they wouldn't look any different to us. So this calculation is counting that as 3 factorial, or 6, different arrangements. But we also have to deal with the Math 2 books and the pre-calc books. So the Math 2 books, there's 2 factorial ways of putting these 2 books in these 2 slots. And there's 2 factorial ways of putting these 2 pre-calc books in these 2 slots. And so instead of, in this problem where we just divided by the 3 factorial because there was just a poster being repeated 3 times, what we're going to have to do in this problem is divide by all of those factorials. We're going to have to divide by 3 factorial times 2 factorial times 2 factorial to get rid of all the repetitions, because this calculation will have lots and lots of sort of extra arrangements that we don't want to have. So after we come up with this fraction, we can put it into our calculator. Now, you have to be really careful because when you type this into your calculator, you're going to have to do the 7 factorial, then the divided by sign, then this bottom part, make sure that you put it in parentheses, otherwise you are not going to get the right answer. So again, let me just say that again. When you put this into your calculator, you want to put the 7 factorial, then you want to divide, put the division sign, and put the denominator in parentheses. So if you do that, let's see what we get. So I got 210. So let's try to generalize this a little bit. So suppose that we have n objects that need to be arranged in a row or line or list, but they aren't n different objects. Suppose one is repeated a times, one is repeated b times, and one is repeated c times. The number of different arrangements would be given by the n factorial that we expect for a row or line or list, but then we have to divide by all these factorials to sort of get rid of the repetitions. Now, you can divide by as many factorials as you want. So like suppose one thing's repeated twice, another is repeated 3 times, another repeated 4 times, another is repeated 5 times. Like you could have more than 3 factorials in the bottom. You could have just 1, you could have 2, you could have 3. However many things are being repeated, that's the number of factorials you can have in the bottom. Okay, so what I would like for you to do now is I'd like you to try out problem number 5. So problem number 5 is a problem about how many different ways you can line up a bunch of yogurts in a row. So I'd like you to pause the video, try out number 5, and then restart the video and make sure that you got the answer correct. So in problem number 5, there's a row of yogurt in your fridge. There are 4 strawberry, 3 blueberry, and 2 vanilla. And the question is, how many different ways are there to arrange the yogurts in a row? So, in total there are, let's see, so there's 4 strawberry, 3 blueberry, 2 vanilla. So that makes a total of 7, 8, 9 yogurts. So we're arranging them in a row. So we're going to start off with 9 factorial arrangements. Then we're going to divide by 4 factorial to deal with the extra times that this number counts arrangements that look the same, since there's 4 strawberry yogurts. Then we're going to divide by 3 factorial and 2 factorial to deal with the 3 blueberries and the 2 vanilla. Again, when you put this into your calculator, make sure that you type in the 9 factorial divided by, and then put this in parentheses. So let me do that out quickly. And you get 1,260. Now, again, if you have decided not to bring your graphing calculator, this is going to get a little bit obnoxious. What you would have to do is you'd have to write out 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 3 times 2 times 1 times 2 times 1. So bring your calculator. And then you would have to multiply out all these numbers, and divide. So make sure that you bring your calculator, make sure that you actually know how to put factorials into it. I promise it will make your life easier. So what I'd like you to do at this point is on the next page there are some more practice problems for you to try. There are answers down at the bottom, so I'd like you to try those out once you finish the there are these ones here, so 6, 7, 8, and 9. Once you finish those problems, make sure that you check your answers against the bottom, and then you can stop there for your homework for tonight. Okay. So good luck in class tomorrow, and I hope that your classwork and homework is going well.